This video is made possible by the support of codenotary.io, blockchain protected authenticity in your DevOps process. Hello everybody and welcome back to the Moshix mainframe channel. This is Moshix. And today I'm going to be talking to you about a speech I gave just last week at an IBM event in Europe. I was invited to give a speech, and the last couple of times that I gave a speech at an IBM mainframe event, I spoke about virtualization, about KVM, about ZVM, etc. But I got bored of always speaking the same thing, and so I said I wanted to talk about the moon landing. And if you followed the videos in this channel, you know that I released a couple of videos about the Apollo guidance computer and the software that was running it. We printed out all the software in the guidance computer from the mainframe in the original IBM 1403 font, and then I also showed how to compile and assemble the Apollo guidance computer software that landed man on the moon in July 1969. And so since it's 50 years since landing on the moon, and it's the whole celebration of that event is still very fresh in our minds, I chose to speak about the moon mission, the moon landing mission, but not from a computer point of view, but rather from a math point of view. And to be more exact, I gave a speech about orbital mechanics, and I decided to tell the audience how to calculate the orbits required to get first from Earth into an orbit around the Earth, and then from there have the translunar injection to get an orbit that will eventually meet the moon. And then, as we know, then behind the moon they had to slow down the command module so that they could enter the lunar orbit, and then they split from the command module into two people, Buzz Aldrin and Neil Armstrong. They split into the lunar module. They decoupled from the command module, slowed down, and landed on the moon. And then later on they took off again, rejoined the command module on the orbit around the moon, and from there then went back to Earth. So I explained that the basis for any Keplerian orbit, something that goes around an object, because of conservation of momentum reasons and many other reasons, then there needs to be an elliptic orbit, and there is a way to calculate the speed at which something needs to move around an object such as the Earth or the Sun or the Moon or whatever, so that to stay in orbit forever and never fall back down again to the object they're orbiting around because of the gravity of the object. So this object has a gravity, and it pulls everything back to it, and then there's a speed at which you need to go around so that you can stay in orbit. And of course the speed is much faster in an ellipsis close to the object you're orbiting, such as the Earth. Here it would be much faster, and here would be much slower, and then speed up again, and this is the orbit that an object naturally will follow in space. And so I explained how this formula here, the square of V, is the gravity, the universal gravitational constant, times the mass of the object, which is about 5.97 to the 24th power in kilograms for the Earth. So it's a very large object. And then this is the distance you want to be from, and this is the average of the axis here. So the average of how eccentric the ellipsis is, so how stretched out it would be. You can calculate the average of the closer one versus the farther axis, and then with this very simple formula you can come to the speed you need to have at any given point to be able to stay in that orbit. And so I showed this by hand on a whiteboard, how to calculate all the orbits. First, how to get to orbit around the Earth, make it a centric orbit or a round orbit, then extend it to an elliptic orbit, and then extend the orbit again with the translunar injection to have that elliptic orbit reach all the way out to the moon. And so we looked at a couple of of this equations and derivations to calculate the moon orbit and everything that happened on the way to the moon and back. I think people liked it, and of course, this being a mainframe event, I later on showed how to put this into a Rexx script so that we can actually have the computer calculate that for us. So I wrote a simple Rexx script called orbit3, and periapse is the closest point from the Earth center, and let's say we want to go on a geostationary orbit around the Earth, so that geostationary means that the satellite will, or whatever object, will be fixed on a point above the Earth. So this, and then to plot it, we can put in 500 kilometer steps. And as you can see here on my ZPDT system here, it calculates then what is the speed that we need to have in any given object. So this speed here is 10.1 kilometers per second, very close to the escape velocity from Earth, which is 10.9 kilometers per second. And then, as you can see, as we go further out, we actually need less speed to stay in orbit. And as we go all the way to geostationary orbit, let's put it in again, and let's do it maybe in 1000 kilometer steps. So it goes from 10.1 all the way to 1.6 kilometers per second. As you can see, it's the difference in speed is striking because of what I said before, which is that in an ellipsis, the speed you need, or maybe we put it like this, the speed you need here is much slower than the speed you will need here, and this kind of shows it. So we put this in a Rexx script and we can look at it. Orbit3 exec. It's a very simple script. First of all, let's start with the square root procedure. We needed a square root procedure that is able to process very large numbers and also very small numbers, which is not that easy. And as you know, Rexx itself does not include a square root function. There are some libraries that you can get which have square root and many other math functions, but usually you will have to write your own. And so here is a square root function that works for very large numbers. And then we input here a default value for apoapsis and periapsis here, and then the height at which we want to orbit around the Earth. These are just default values so that we don't have zero value equations. And then the step will be 100 kilometers per step. And then we ask the user to input the periapse, which we just saw, how far from the center of the Earth, and then the apoapse from the Earth center, the increments, and then this is the distance from the average distance from the surface of the Earth to the center of the Earth, and so we calculate all those distances to the center. And then here is the formula that we just saw on the screen. Here's the formula. You will recognize it here from this thing here. This is exactly this formula. So we call this function for each step as you can see here, we step through from the periapse to the apoapse, and each time we pass the velocity and the step. So then it can call this function, and it calculates it, and then returns the value. And so here it says at orbital altitude I, the required velocity is whatever the result is from this function, meters per second. So this works just fine. As we saw, we can run it again. So if I run it again, we do it in 1,000 kilometer steps, it would you just execute the code we just saw. At each interaction it calls the vel function, and then within there it will have to call the square root function that we saw. So it's a very pretty script, very simple. And of course I wanted to this is, you know, if you show this to people who started programming in the last 10 years or so, doing this on a black screen is just on a terminal, it's just not very user friendly. People want to see something ideally within the browser, ideally with a graphic plot. And so the question was, how can we make this script without any changes plotted on a browser? Or another way to say it, how do we go from this let's do it again, from something like this, how do we go from something like this to something like this? Okay, I'm just showing you the end result here. So this is in a web browser, and it shows a plot, and I have the input values here, and then it plots, and then I have the same thing that we saw here, but now in a much nicer format. And so how do we go from that to this? And if to get from that to this, first we need to have something that processes this output on the mainframe, and then I wanted to have a program for Linux on the mainframe to produce this output so that we could connect from anywhere in the world with any browser and look at the plot of the orbital velocities. So that's what we need to do. So the first step is easy, because the first step just requires this one simple Rexx program, and to produce any JSON output from the Rexx program, which then my Go language program could receive and plot on a browser, we needed to turn to my friend Sebastian, who's done this before and has shown some videos in the past in this channel, how to get things written in Rexx to produce output that can be viewed anywhere. Sebastian, I just met him last week also in Europe. We both gave a speech at the same mainframe event. He is well known because he won 2 times the Master the Mainframe competition of IBM, and also won the worldwide Master the Mainframe competition. So he's and he also owns his own IBM Z9 mainframe, which he runs in his own cellar at home. So he's one of only 3 people or so who have a real mainframe at home and are running it successfully. So Sebastian, why don't you show us how we make this become something that will produce something suitable for a web browser to plot on the screen. Over to you, Sebastian.
Moshix sent me his Rexx script, and he wanted it to be processed on the mainframe but displayed on his web server. So we could use the web enablement toolkit for this on ZOS, but as we don't have it, there was only one option, and that was using DB2 and using DB2 stored procedures. So you need some prerequisites for this. You need a VLM application environment, because the Rexx script is not running in TSO, it is running in the VLM environment. In order to get that, you can run the SAMP job, and this is located in the SDSN SAMP dataset. The name is dsntjmv. And you have to use the environment when you are defining the stored procedures to DB2. Now, the second thing is you need DB2 native REST service, and this is available with the DB2 version 11 or v12. It is activated also by a SAMP job. This one is dsntjrs, so you have to submit this. And if it was successful, you can restart DB2 and start binding services to it with the job or with the service manager. So that's what you have to do in order to do the same stuff. So we are now on our main frame. Moshik sent me his Rexx script, and I put it in the SDs and CList dataset, and that's the system dataset that is known to DB2 to store all the Rexx stored procedures. So let's just search for it. So now we have multiple datasets. We use the version v12 as I said. So let's browse this dataset, and yeah, you see that's just me putting those members inside, because normally you wouldn't edit some system libraries, but that's the fastest way to set this up. Okay, let's view his code. That's the old one. Refresh. Okay, I think orbit 2 was the actual one. Let's view this. Okay, so now this is his code. He has his input parameters, and I didn't have to change a lot. It's basically everything's the same, just the output changed a little bit, because this is not saying anything or printing out anything. It's just returning the out variable. And now we can look how to define this piece of code to DB2 as a stored procedure. So let's go back and let's see our SQL. So this is defined by SQL to DB2, and I use Spoofy for this, so let's look at the members inside there. So that's the member with the SQL code. Now here we see it. The first line was just for trying out, so I had to drop something. This is where I create the stored procedure. You see all the in variables. I just set them to 20. It doesn't matter really. And the output is the return string we saw in the Rexx script, and just set it to 255 because this will be enough for any possible output, most likely. So the external name orbit 2, and there we see our VLM environment, and that's it. So we can set this up using Spoofy. Can show you how this one works. So Spoofy is normally under more and DB2. So this is where you get to Spoofy on a normal way, but we have two DB2s installed, so we modded something up, and it's located in this dataset. This was my Spoofy. We can look at the defaults. These are the settings you have to insert here. You need the subsystem identifier. When it looks like this, it's okay. And go to 1. And here we have our input dataset names. These are this is the member I used. This is where the SQL code is stored. So what we saw. And then you can enter an output dataset. This must be a sequential dataset. This is basically storing the response of the DB2. So you really just need those two datasets, and then you can start off. Just press enter, and there we see our code. In this case, it is the same member I showed you. So I won't execute this because the procedure already exists, but it should say 0 and successful, and we are done. So I just go back, and the next step was to do a REST service out of that. So we have to bind a REST service on that stored procedure, and in order to do that I use the bind job, which is also a SAMP job that you can find if you want to use the DB2 native REST service. And let's go inside. That's the one. So this job basically binds the package, and above here we have to insert our library. There are some names that will be displayed when we call the service or the service manager to identify it. But the most important thing is this one. So here we call our stored procedure that we defined with the SQL, and it works like this. We just call it, and there are some variables, and those will be passed when we call it through our web server, and then that's basically it. Okay, one question will most likely be, how can we see the REST service, how can we call it? And therefore we go into the active users and search for the DB2 master address space, so pre mstr, and there we see it. We use the we used D121. Let's look inside. Where it started, and there it says where it's listening to. So the TCP port is 4012. Okay, now we add to our host name just the port 4012/services, and we will get prompted for the user and password. And after that we see all the services that are defined to DB2, and we can use them over their URL, and it will respond like any REST service, so it's perfect.
Well, thank you, Sebastian. That was clear. So what Sebastian did is he showed us how a Rexx script on ZOS can, through DB2 and this DB2 spoofy interface, create a JSON output on a port, which then I can write into and obtain result back. So why don't we do this is the query that I would launch, right? I'm just using curl here because it's a simple way of just simulating a web browser. See here from curl. So if I give it this this query, I will get the result back. As you can see here, altitude, velocity. So it calculates a velocity for a given output and eccentricity of an ellipse or elliptical orbit. So now, given that I can just send this to DB2 on ZOS and get this response back through the Rexx script that I sent to Sebastian, now we can start thinking about how to make this turn into this, what we have here, right? Because what we're doing here is just sending a number of queries, and of course we could optimize it so it does it all in one query, but right now it's the exact same Rexx program that we had before, and so I just wanted to show that it's possible to take a Rexx program and leave it as it is and produce something like this, right? So what it does is it takes this input and then goes to the outward range by this increment, sends for each increment a query to that JSON interface, it gets the output back, and then the Go program plots this. The only twist here is that since we're mainframe people, I wanted to run all of this on the mainframe, and so this is a Linux running on a mainframe at the University of Leipzig. So if I do uname-a, you will see that this is Linux running on a mainframe. We can also do it something like this. And you will see that this is an IBM S390, 2 processors, 10,000 BOGO MIPS. So I'm running on 2 processors here. And so we're running this on Linux, but Linux is just a Linux. Linux on the mainframe is just another Linux, just more reliable. And what I did is we, together with some folks I work with in the office, we wrote this Go language program, which basically does what I just showed you. It just exposes an interface, which is I can call from any browser, and then here's the part that goes to that address that I just showed before and sends the query with those values that we're building here from here, and sends it, and then gets the response back. And there is a package called static, which allows us from values to build tables, little plots like this one. So very, very simple. And if I go and count the number of lines, we have, oh, it's counting the binary, but if I just count the Go, 77 lines, including all the comments and all the empty lines. So in only 77 lines we wrote this, talking to the mainframe. And that's the beauty of both Go, and it's the beauty of Rexx. My Rexx script is maybe another 30-40 lines. So with 100 lines we build an orbital plotter. That's as simple as it is. So the way I run this is I just we can of course build it, say make Rexx orbit, pay attention here, this line, and this goes and builds it. And we are almost done. It's actually taken a little bit. Yeah. So now it's compiled the Go script into binary, and here's my binary here, and I run it by just saying Rexx orbit. And now here we can access it, and I can give it, so let me see. Yeah. So if we go from this kind of orbit to this kind of orbit, so well, this is a little bit, makes no sense to go to the surface of the Earth, but and we do it in 200 kilometers increments. So here you see that it actually also reports all the output if you want to see it all. So then we produce this, right? So this is a plot, and just the velocities that you need to have at any given of those altitudes of a spacecraft or satellite orbiting the Earth. So this of course is for the Earth because of the mass of the Earth that we put in. We could also have here an additional field which gives us ask for any other body such as the Sun or the Moon, and then have the masses for those planets stored, so that it can then calculate for any given body that we want to calculate an orbit for. And so this shows how easy it is to go from something like this, right, to go to something like this. It can all be done in like half an hour. And so that's what the speech was about at the mainframe event in Europe. And so thank you, Sebastian, for showing how to work the IBM ZOS and DB2 spoofing interface to produce JSON. And thank you for all the various books I consulted on orbital mechanics. There's one called Astrodynamics this one, Fundamentals of Astrodynamics. This is a book I would recommend if you're interested in the topic. It explains everything there is to know about how to deal with these things. And I used this book for a project I had ever since I was 13 years old and visited my cousin at the university in Australia because he was studying astrodynamics. And my goal was once in life to be able to calculate find out if and when all the planets will be lined up in one line from the sun to the last planet. And so using this book I was able to calculate it, and all I needed was a little bit of Rexx programming. But anyway, so this shows the power of the mainframe, and this has been incredibly stable. I've been having this running for about a month or so. It's just always there and works. And I'm going to shut it down now. But that's it. If you want to look at it again, this is all there is to it, right? Very, very simple. And this produces this. So if you have any questions how to get this done, if you want to see the source code, if you want to help with setting up your own go to Rexx interface on ZOS, then please let me know. Post any comments below this video. Sebastian or myself, I'm sure, will be happy to answer any way we can, and wish you a pleasant day. Goodbye.